Hi, my name is John Stevens, and I'm going to tell you about a tool called SmartPulse, which was developed with Kostas Verlez, Benjamin Mariano, Shivandu Lahiri, and Ishal Dillig. So cryptocurrencies and smart contracts have become increasingly popular over the last couple of years. In the last couple of months even, we've seen NFTs becoming popular in pop culture, cryptocurrencies including Ethereum hitting an all-time high in price, and users having the ability to pay for more and more goods using cryptocurrencies. However, this has come at a cost as buggy and malicious contracts have become increasingly impactful. So over the last couple of years, we've seen hacks such as the DAO hack and the parity hack, and each one of these has cost users millions of dollars worth of worth of Ethereum in this case. At the same time, we've also seen a number of bugs within smart contracts which may freeze currency within that contract, and the users therefore don't have access to currency that they should otherwise be able to access. So we can group these bugs together based off of the type of property that they violate, namely if they violate a safety or a liveness property. And as you can see, in the past, both types of violations have occurred. So a safety property states something bad never happens, whereas a liveness property typically states something along the lines of something good will eventually happen. And so the real difference between a safety and a liveness property is a safety property is violated in finite time, whereas a liveness property is violated in infinite time. So an example of a safety property would be the highest bidder in an auction can never collect a refund, whereas a liveness property would be if I'm outbid, I can eventually collect a refund. And this is a liveness property just because even though I haven't been able to collect a refund in the past, doesn't mean I won't be able to in the future. And so the problem that we run into is there are many automatic tools to check safety properties in smart contracts, but no automatic tools to check liveness properties in smart contracts. This is where SmartPulse comes in. So in order to use SmartPulse, users will specify the property that they wish to check in our Smart LTL specification language, and they'll provide the Solidity program that they wish to check. And then SmartPulse is going to check the conformance of that program to the Smart LTL specification and eventually say, yes, this property holds, or no, it doesn't, and here's why. And it does so using two generic steps. The first step is to instrument the program, and the second step is to check the instrumented program using a software model checker. So let's take a look at an example auction, which we'll continue to look at throughout this presentation. So here, the auction allows users to bid in the auction, and the auction will keep track of the current highest bidder, the amount that they bid, and any users that need to be refunded because they have been outbid. In addition, the owner can decide to close the auction, and then the owner can also issue refunds to everyone who is outbid. So something that a user might wish to know is if they bid in this auction and are eventually outbid, will they eventually be refunded after the auction is closed? And this is a liveness property. So if they want to use SmartPulse in order to check this property, they would first have to specify the property in Smart LTL. So that's what we're going to look at right now. So the first thing that they have to do is specify an equation, or they have to write an equation in our Smart LTL specification language. And so this language has the normal temporal operators that you would expect to see from LTL, including next, always, eventually, and until. However, when we start to look at atoms, things look a little bit different. Namely, you see these functions that take two arguments. In general, or generally, the first argument is going to be the name of a function, and the second argument is going to be a constraint that the user wishes to hold. And we'll talk about how each one of those is evaluated a little bit later on. But the constraints of the program can be specified in first order, quantifier-free logic. And in addition to the normal operators that you would expect to see there, we include a couple of functions which is supposed to aid the user in writing certain types of specifications. Namely, we provide a csum method, which will take the sum of a collection, like a map or an array, and an fsum method, which will take the sum of a value over time. So now let's go back to that specification that we looked at previously. And this is how we would write that specification in Smart LTL. Namely, what the specification says is if I successfully bid a value of X, and eventually the auction closes and I am not the winner, then I should eventually be sent an amount of money equal to my bid. So the way that we're going to use Smart LTL is we are going to individually check traces within the program to see if that individual trace conforms to the specification or not. And so let's take a look at how that would work. So here you can see a trace through the program where the user calls bid, then eventually the owner calls close and tries to refund everyone who was outbid. So what we're going to do is we're going to take each one of those atoms, and those atoms specify a particular point in the program where we want to check the constraint. For example, the finish bid atom specifies that once bid has successfully executed, we want to check the constraint that the message value is equal to X and the message sender is equal to L. And it's the same for the finish of close and the send constraints. And so what we're going to do is we're going to iterate through all of the programs within, or iterate through all of the traces within the program. And if all of them conform to the specification, then we have verified that it holds. And if we find a trace that does not conform to the specification, we found a violation. So let's take a look. Now that we know what the inputs are, let's take a look at the steps used to do this. So the first step is to instrument the program. So in this talk, we're only going to look at this instrumentation step, which is converting smart LTL to LTL. And this step is going to take in a program and a smart LTL specification. It's going to produce a modified program and an LTL spec. So the way that we're going to do this is we're going to take in a smart LTL specification, and we're first going to instrument the program with fresh Boolean variables. And these Boolean variables indicate the satisfiability of a particular atom within our smart LTL specification. In particular, if you look at the highlighted atom, this is how we would instrument that into the program. So basically, we would create a fresh Boolean variable, and we would set the value of the Boolean variable to be equal to the constraint specified by the user. But then we immediately set the Boolean variable to false. And the reason why we do this is because we're going to instrument it into a location where the constraint is only checked if bid has finished executing successfully. And so this means that everywhere in the program, besides that one particular point, this Boolean variable is going to evaluate to false. And this is the way that we want that atom to behave. So the next thing that we're going to do is we're going to express our smart LTL specification in terms of these instrumented variables. And if we do that, we get a typical LTL specification. So the rest of these variables that you see there are similar to the ones that I showed above, but for each one of those atoms. So the next thing that we're going to do is we're going to send this to a typical software model checker. In particular, we're going to use a cigar-based method like the one used by Ultimate Atomizer in order to get particular example traces, and then we're going to evaluate whether or not the specification holds on that trace. And so the way this is going to work is we're first going to take in a program and a specification, and then we're going to construct a Buki automata by combining the program and the specification. So essentially, any path through this new Buki automata is going to consist of paths that might violate our specification. And so if we end up finding that our Buki automata has, so the first thing that we're going to do is we're going to check to see if our Buki automata has any such paths that might violate our specification. And we're going to do that using an emptiness check. So if the emptiness of our Buki automata, or if our Buki automata is not empty, then we're first going to get a path from that automata. And then we're going to check if that path is terminating. If it is non-terminating, we found a valid counterexample because we found an infinite trace. If it is terminating, however, then we can simply remove that path from our Buki automata. And we're going to keep doing this until eventually our Buki automata becomes empty, or we have no more paths that could violate the specification, in which case we have successfully verified the program. So in addition to this, we have modified the cigar-based approach in order to simplify these two checks within the verification algorithm. Namely, we use domain-specific knowledge to help us check whether a particular path is non-terminating or terminating. And if you'd like more information on this, I would encourage you to go and read our paper. So now let's take a look at our evaluation. So in order to evaluate this, we wanted to answer a couple of research questions. The first of which is, can SmartPulse actually verify liveness properties? So in order to check this, we gathered a number of smart contracts from prior work, from important repositories like OpenZeppelin, and from the blockchain. And then we constructed a number of properties that we would expect that to hold within that contract. For example, the property that you see here is one that we checked, which says if a crowd fund is finalized, then eventually a user should be sent an amount of money equal to the sum of the tokens that they bought. And this in particular is if a crowd fund failed to be funded. So we checked a number of contracts. We checked 9 contracts against 34 total properties, and we were able to verify 26 of those properties and falsify 6 of them. And it took on average about 10 minutes. So altogether, SmartPulse was able to verify or falsify 94% of the liveness properties that we looked at. The next research question that we wanted to consider was, how does SmartPulse compare against existing verifiers? And so we took a look at 2 particular tools that are available to check safety properties within smart contracts, namely VerX and KEVM. So VerX takes in a safety temporal property, and it uses user-provided predicates to aid in verification. So we checked VerX against a variant that uses these user-provided predicates and a variant that uses no user-provided predicates to see if they can, or how well they can verify properties automatically. In addition, we also checked SmartPulse against a tool that uses KEVM's Ethereum blockchain formalization in order to verify method pre and post conditions, and we call that KEVM-Ver. And so our first comparison against VerX evaluates SmartPulse against all of the smart contracts and properties that VerX evaluated against in their paper. And we found that SmartPulse was able to verify more properties than both the version of VerX that uses user-provided predicates and VerX without any user-provided predicates. So SmartPulse is able to verify more properties in similar time. In addition, when we evaluated against KEVM, we checked 151 ERC contracts using KEVM's formal specification of the ERC20 contract. And so each one, or the formal specification contained 12 properties, and so we checked a total of 1,812 properties. And we found that KEVM was able to verify and falsify fewer properties than SmartPulse. And so in total, SmartPulse verified 233 more properties in less time. Our final research question was, can SmartPulse generate attacks against vulnerable contracts? Because SmartPulse will generate a counterexample, we want to make sure that those counterexamples can be used as legitimate attacks. So here is the option that we considered earlier. And so now let's see what a counterexample to this would look like. So here's a trace that we might get from SmartPulse. First, an auction is created with an owner equal to Bob, and then Eve is going to bid a value of 15. Then Alice is going to come in and bid a value of 16. And finally, Claire is going to come in and bid a value of 17. And then finally, Bob is going to close the auction. And then because Bob is a nice guy, he's going to try to refund everyone who had bid within the auction. However, and so Bob is going to iterate through all of the bidders and try to send them the money that they are owed. However, when he tries to transfer money to Eve, Eve reverts, which essentially causes the way that the Ethereum blockchain works is if a revert occurs, then it's going to revert all of the changes made during that transaction. So basically, it will be as if this refund call never happened. And so that ends up causing the entire transaction to revert, and therefore no one got their refund. And then if we try executing that entire sequence again, because Eve is always going to revert, that entire transaction will avert no matter how many times it's called. And so we found an infinite counterexample. And so SmartPulse counterexamples can correspond to attacks from prior work, and we were able to get SmartPulse to generate attacks corresponding to reentrancy, gas, denial of service, and overflow attacks. In summation, SmartPulse is the first tool to check liveness properties in smart contracts automatically. It can verify safety properties better than prior work, and counterexamples can demonstrate attacks on smart contracts. And that is the end of my talk. I encourage you to all read the paper. Thank you.